Welcome to MATH2030 Combinatorics. In this video, we're going to talk about Chapter 2.1, 2.2, Sum and Product Rule, and Chapter 2.3, 2.5, Permutations. Let's start with the rule of products and sums. So the rule of products says, suppose a procedure can be accomplished with k disjoint subtasks. If there are n1 ways of doing the first task, n2 ways of doing the second task, so on and so forth, and n sub k ways of doing the case task, then there are n1 times n2 times all the way to nk ways of doing the overall procedure. Let's take a look at an example. The ternary numeral system, which is also called base 3, had 3 as its base. It often refers to a system in which the 3 digits are all non-negative numbers, specifically 0, 1, and 2. A ternary work is a string of ternary digits. First question, how many ternary words have length 3? Well, so when you think about coming up with a ternary word with length 3, all we need to do is to fill up the 3 spaces. And when we fill up the first space, we had 3 choices, the second space, 3 choices, and the third space, 3 choices again. So in total, we have 3 to the power 3, which is 27 ways or 27 many ternary words that has length 3. How about the second part? How many ternary words have length 5? You probably know the solution to the second part. It's very similar to the first step. Over here, we are trying to come up with ternary word of length 5. So we have 5 spaces to fill, and each space we have 3 choices. So it's going to be 3 to the power 5. Okay, so that's all good. Next, we're going to talk about the rule of sums. If an event E1 can be done in n1 ways, and another event E2 can be done in n2 ways, so on and so forth, until the last event E sub k, which can be done in nk sub ways, and these events are all mutually exclusive, then the number of ways of all the events occurring is the sum of these n sub i's when I runs from 1 to k. Let's continue the example we just did. So the setting here is the same, but the question becomes, how many ternary words have length at most 3? Well, if you want to come up with a word that has length most 3, that means sometimes this word may have length 1, sometimes it may have length 2, and sometimes it may have length 3. So there are 3 possible cases that might happen, and we can find out how many words are there in each one of these cases. So let's start with the first case. How many ternary words are there have length 1? Well, that's apparently 3, because we had only 3 choices. And the next case, how many ternary words have length at most 2? So we're back to the first example. You think about the number of choices for the first space, and then think about the number of choices for the second space, which is 9. And then the third case, we've already talked about it. So it's 3 times 3 times 3, which is 27, which means in total, the number of ternary words that have length at most 3 is going to be 3 plus 9 plus 27. And that gives us 39. So that's the rule of sums in play here. All right, let's move on. The next example, how long must an identity number be in order for there to be at least 7 billion different numbers, assuming none of them starts from 0 or 1? So in this question, we don't really know how long this identity number could be, which means there are a few places that we need to fill up, and we want the number of choices to be at least 7 billion. So we want the number of choices to be greater than or equal to 7 billion. So if I assume that there are n many places for us to fill up, how many choices do we have in total? Well, for the first place, we know that we have 8 many choices. So in theory, you could fill up any of this place by number 0, 1, 2, all the way to 9. But because the first place was already assuming that we cannot use 0, we cannot use 1, so we're only left with 8 choices. However, for the rest of the places, they all have 10 many choices, which turns out to be 8 times 10 to the power of n minus 1. So this is a total number of choices we could have if we know that this number has n many places, n many digits. And we want this to be greater than or equal to 7. 7 billion is 7 times 10 to the power of 9. In other words, as long as we know that n minus 1 is greater than or equal to 9, we're good. So in other words, this number must be at least 10 digits long so that we would have 7 billion different numbers.